Hello, everyone. My name is Sagar Sen, and I'm a student of BSc Honors Data Science and Artificial Intelligence program at IIT Guwahati. Today, I will be presenting my internship one pro project course code DA377, and the project that I had been working on is AI-enabled hybrid LiPo lithium-ion power management monitoring system for FPV quadcopter simulation base. This project focuses on intelligent energy management using an AI-inspired decision system. Now, the problems and motivation behind this whole project was that FPV drones operate under highly dynamic load conditions, depending on flight phases such as takeoff, maneuvering, and landing. Traditional systems rely on single battery, which creates the fundamental limitations and are inefficient and unreliable. LiPo batteries provide high power but have low energy density, while lithium-ion batteries provide high energy but cannot handle high power demands efficiently. This creates a trade-off between performance and efficiency. Existing systems lack intelligent decision-making under dynamic conditions. So the goal of this project is to develop a AI-driven adaptive energy management system that dynamically selects the optimal battery based on real-time operating conditions. Now, the tools behind this whole project uh, is that this system is implemented entirely in MATLAB using a simulation-based approach. The simulation models a complete mission profile, including takeoff, cruise, maneuver, and landing phases. The inputs include load current from 1.5 amp to 24 amp dynamic range, weather and environmental disturbances such as wind, and aggressive maneuver conditions to simulate real-world variability. The system uses two battery types, LiPo for high power output and lithium ion for high energy density and capacity. Since this is a simulation-based system, no external dataset is used. However, the simulation captures realistic variations in operating conditions. And now the code implementation. The system is implemented using a discrete time simulation loop. It includes detailed battery models that track state of charge, voltage behavior, load current, temperature dynamics. At the core of the system is an AI-inspired rule-based expert system, which acts as the decision engine. This system evaluates the multiple parameters in real time, including load, SOC, voltage, temperature, and mission phase. The decision-making follows a priority-based hierarchy where safety-critical conditions such as low battery or landing override all other decisions. Additionally, hysteresis logic is implemented to ensure stable switching and prevent frequent oscillations between batteries. Overall, this system performs interpretable and context-aware decision-making similar to an expert system. Now, the results and outputs from this project, the system produces real-time outputs through a telemetry dashboard. We observe SOC distribution across both batteries, voltage and temperature variations, dynamic battery switching behavior. This system ensures optimal trade-off between performance and efficiency. The key insights is that lithium ion is used during low load cruise phases to maximize efficiency, and LiPo is activated during high load and safety critical phases such as takeoff and landing. This demonstrates that the system can dynamically adapt across different mission phases. Overall, the system ensures an optimal trade-off between performance and efficiency. Now, let me walk you through the complete code that has been implemented using MATLAB. So this is the whole program that includes all the AI-enabled uh, features. These are all the features that has been implemented throughout the program. The input conditions, flight profile, battery parameters, environmental factors, aggressive maneuvers during the flight durations. All these conditions has been implemented in this throughout the program and the decision logic. So, and the outputs, it gives outputs as the intelligent battery selection between lithium, LiPo and lithium ion over time, state of charge evaluation for both batteries, voltage and temperature profiles under dynamic load, battery switching behavior and decision traces, and real-time telemetry dashboard for performance visualization. So all the decision logic has been implemented throughout the program, and it includes all the AI-enabled key features and the logics that has been implemented in this throughout the program. And um, this is all. This is the whole code for the project that has been implemented. And now let me run you through the simulation, the complete dashboard that is generated from this uh, program. So here's the complete dashboard that is generated, and it includes the LiPo battery uh, battery parameters, lithium-ion battery parameters, 3D drone visualization, um, and flight time. It also calculates the flight time estimation, um, and the drone mission control start, reset, and exit. And the real this is and the program also includes the real-time telemetry dashboard that monitors load current, battery voltages, state of charge, battery temperature. Now this is a interactive dashboard. And in as you can see, uh, um, the it shows the drone in a real time uh, feed. And so as soon as you start the mission phase, the drone takes off, and then throughout the flight duration, it constantly switches between two batteries, LiPo and lithium ion. Now, I will walk you through the the decision logic that has been implemented throughout the program. So here's the whole decision logic that has been implemented throughout the program. So from start till end. So the uh, the drone uses and con uses the batteries, both the batteries, and constantly switches between the batteries throughout require as per the requirements and the flight conditions. So whenever there is a requirement for current load greater than 8 ampere, it uses LiPo battery, and whenever it requires less than 8 ampere current, it uses lithium ion, and based on that, it constantly manages the uh, the um, constantly manages the batteries and battery usages. And at some point, so once the battery starts draining, the LiPo battery is reserved at 10% for uh, for landing and for emergency, and then it uses lithium ion battery for rest of the flight duration. And so as you can see, the whole decision logic from start till end. And during the whole trials, I'll walk you through the trials that we went through. So as you can see, this is the end of the simulation. Lithium-ion battery uh, has been drained till almost 11.4%, and LiPo battery is completely drained by the end of the mission. It, this battery system basically dual battery system basically reserves the lithium-ion battery uh, and cuts off the usage at around around 10%, 10%, 10 to 15% SOC, so that it doesn't completely discharge the lithium-ion battery for safety purposes. Here is in between the simulation. As you can see, the LiPo battery has been cut off at 10%, and the battery is reserved. And then for rest of the flight duration, the drone uses the lithium-ion battery. And now back to the uh, presentation. And so the evaluation matrix in this project. Since this system level simulation, evaluation is based on performance and behavior rather than traditional machine learning metrics. We evaluate the system based on the efficiency, energy utilization, stability and decision behavior, stability of switching, decision consistency under dynamic conditions, response time to critical events, safety concerns, operation within safe voltage and temperature limits, and measured level performance include return to base triggering, emergency landing, and these metrics ensure that the system is not only efficient but also safe and reliable. And now, conclusion and future work. This work demonstrates the feasibility of AI-driven energy management in UAV systems. The AI-enabled rule-based decision engine enables real-time and context-aware battery selection. It performs multi-parameter reasoning using SOC load voltage, temperature, and mission phase. This program demonstrates interpretable AI for safety-critical UAV systems. This approach shows how interpretable AI can be applied to safety-critical systems where transparency is important. The hybrid system improves energy efficiency, adaptability, and operational safety. It also establishes a foundation for future intelligent energy management systems. Now, the future work in the future, the system can be extended using advanced AI and machine learning techniques. This includes reinforcement learning for adaptive policy learning, predictive models for battery health and energy demand, time series forecasting for mission-aware optimization, mission-aware energy optimization, transitioning from rule-based to learning-based system. Additionally, the system can be deployed using edge AI on embedded UAV hardware. It can also be extended to multi-drone systems where energy management is coordinated across a swarm. Thank you for your time. This project demonstrates how AI can be effectively applied to real-time energy management in UAV systems. I hope you found this presentation insightful.